Okay, for those that are already here, thanks for joining me. This is the Triple C 10 exam. Before we get started here, we'll start in uh, 3 to 4 minutes here. If you guys have any questions in particular, maybe some topics of concern you guys have, which you would like to be talked about in particular, you can post that in the chat. I try my best to monitor the chat and please, interrupt me. Problem to ask a question. Only if you have a question. Also have questions. That's what this exam is. Exam reviews here for I want you guys to ask questions. We'll get started soon. And also, if you guys can hear me right now, just let me know in the chat. Hear you. Audio sounds fine. To that nature. See, some more people are joining now. Joining me now. EECE 2310. You guys can hear me, just let me know in the chat. I try to monitor the chat. There's a little bit of latency between sending a message and me saying it, so just keep that in mind. And before we start here in about 3 minutes, just let me know if you guys have any topics you would like to go over. In particular, um, I've I'm old now, so I've Dr. Nikoubin was not here when I took 2310, so I'm not entirely sure this class differs from how I took the class, but I'll just be going over some general topics, right? And if you guys want something more specific, just let me know in the chat. That. All right, it's 3 past the hour. I think we're gonna get underway here. So, I think the first thing to go over in this class, particularly, is the binary number system. You can't really do much without knowing binary. So, I'm just gonna go through a quick run through, how binary works, and then we'll work a few example problems, such as converting from binary decimal to hexadecimal and to octal, and all the different ways in between there. Do some addition and subtraction examples. And I'll talk about fixed point notation. So, in later classes, you'll learn about floating point, IEEE 32-bit floating point implementations. But for this, we're going to stick with the fixed point and how to represent fractional numbers in binary. So I'm just going to give a very brief synopsis. You guys probably already know that. So binary, we use ones and zeros, right? Represent numbers, right? Humans, us, we have 10 fingers. We represent things in base 10. So you may have a number 29. But digital logic needs to be flipped on and off. So we represent things using zeros and ones. And how the binary number system works is, you have a binary number here, say this binary number. And every place represents some power of 2. So this first place will represent 2 to the 0. This will represent 2 to the first, to the second, and 2 to the third, and this goes to 2 to the n, where n is the number of bits you have. And so if we have a binary number, say this number, that should be a 1. Oh, I put a 3 there. If you have some binary number here, and I wanted to convert it to decimal, right, I would just use these places to figure out what it is, right? 2 to the third, 2 to the second, plus 2 to the 0, right? So this is 8 plus 4 plus 1, which is equal to 13. So this is the general way we're going to convert from binary to decimal, and vice versa. Kind of keeping this in mind, and when you do enough of these problems, you'll recognize, oh, the fourth bit is 8 and the third bit is 4, right? That'll come quickly once you do enough of these problems. You won't have to write down all these place values, but that's just me trying to explain how this is going to work. So let's just, for fun, do a couple examples going from binary to decimal. And after we do that, we'll talk about hexadecimal here. So I'm just going to create some random number. I'm going to just use an 8-bit number. So I just created some random 8-bit number here, and let's convert this into decimal, right? So like I said, you can think of each place as some representation of the power 2, right? So this is 2 to the 7th right here. This place right here is 2 to the 0th. Place in between you have, right? So 2 to the 7th, you just look at each bit and kind of add up all the bits. So 2 to the 7th is 128. So we have 128. This place is 64, right? But there's a 0, so we're not going to add that. 32 and 16 are right here. So let's add 32 plus 16. We have 8 here. This is 2 to the third, right? Which is 8, and this is 2 to the second, which is equal to 4. So all you have to do is add up all those numbers, right? So this is 10, 20, 28. This is 4, 78. Just double check my. Yeah, we got 20, 32, 16, 8. It's supposed to be. This was 2 to the 1, actually, which is just 2. That's where I messed up. All right, let's go back. So this was 6 here. Yeah, sorry about that. So let me redo this just for clarity's sake. Just made a mistake there. So right, 2 to the 7th here is 120. So this is the 7th place, right? This bit right here, that's 2 to the 7th, which is 128. This one's 2 to the 6th, right, which is 32. This bit's 16. This bit's 8. This bit's 2. And then we just find all those, right? And add them all up. That's 6. 2, 4, 7, 8. So we get 186. And so that's the conversion from decimal, from binary to decimal. So let's do something the other way around now. So how about we go from a decimal number to a binary number? Let's say we want to convert 56 to binary. I want to use 8 bits, right? It's pretty standard. So the way I like to do these problems when I have to do a decimal to binary conversion is I like to think of the biggest power of 2 that can go into my number. So, in my head, I think of powers of 2, right? You have 0, 1, 2, 4, 8, 16, 32, 64, 128, 256, so on. So what's the biggest power of 2 that can fit into 56? Well, I know that 64 can't fit into 56, but 32 can. So like 2, right? That's my first place. And then I think of the next lower power of 2, which is 16. So if I add 16 to 32, will I get more than 56? No, in this case, right? So I'm going to add 16, right? So now we're up to 48. So what's the next power? It's 8, right? 32, 16, 8. Can I add 8 to 48 and get 56? Well, if I do that, I get exactly 56, right? So I know I have a 32, a 16, and an 8. And that's the ones I'm going to write in my binary numbers. So I'm going to go, right? This is 32. This is 16. This is 8. I had nothing in the 4, nothing in the 2, nothing in the 0. And I said I wanted to path this up to 8 bits, so we add leading zeros right here, because this was, right, 128, we didn't have 128, and this is 64, we didn't have any 64. So this is our binary number right here. This is how we would write this, 56 in binary. I think everyone should be with me so far. This might be a little basic to some people, but we can get it out of the way just to make sure everyone's on the same page. So All my examples I've kind of shown you here have been with binary. So there's two other different types of number systems. One is called hexadecimal. So let's go through that. So how hexadecimal works is you have, and binary number systems, you typically have things called bits and bytes and nibbles. So this is 8 bits. Each binary symbol here is called a bit, and a nibble is a grouping of 4, right? This is the nibble, and a byte is typically 8 bits, right? So what hexadecimal does is, writing a long binary number takes up a lot of space, right? So what hexadecimal does is it expresses each nibble as a symbol, and it's 0 through F, because 1 through 9 and then A through F, that's 15 values, right? And I know that to calculate the maximum number for a binary number, it's 2 to the n minus 1. So 2 to the 4 bytes, or 4 bits in a nibble, minus 1, that is 16 minus 1, which is 15. So that's how I write it, at this 15 different symbols. And what I mean by that is, let's say we have this nibble right here. How should we convert this into hexadecimal? Well, let's think about what this number is. It's 8 plus 4 plus 2, which is 14. And A through F, A, B, C, D, E, F, this is 10, 11, 12, 13, 14, 15. So if I want 14, right, I'm going to pick E. So this is hexadecimal E, this binary symbol right here. So we're going to use this to do some conversions. So let's go back to my example here. This binary number, and I'm going to take every grouping of 4 bits, and I'm going to convert it into some hexadecimal symbol here. So let's start with this first one. In my head, convert it to binary, right? Something I can understand more easily. So this is 8 plus 4, 12. And 12 in hexadecimal is C. Right? Because A, B, C, D, E, F, 10, 11, 13, 14, 15. Okay, so let's do this next one. I did this previously, right? This is 8 plus 4 plus 2, which is equal to 14, and 14's E. So how we write this binary number, we converted it to hexadecimal, and typically when you're expressing hexadecimal numbers, we write 0x in front of the number. That lets you know that this is a hexadecimal number, and we are going to say that this is the expression C. So let's maybe do something different now. So, and remember, at any time if you have questions, I'm looking at the chat. Let's go from the other way around, hexadecimal to binary, and then back to decimal, just for the fun of it. So I'm just gonna make something up here. This, right? So we want to convert this into binary now. So let's work this out. Remember I said that every hexadecimal symbol correlates to 4 bits. So our final answer should be 12 bits long, right? So let's do this 9. We're just going to represent 9 as a binary number, 4 bits. So I'm thinking to myself, what's the highest power of 2 that can fit into 9? Well, I'm thinking 8, right? So we have 8. These two are 0 and 1, because I need one more. 8 plus 1. gives me 9. So that's that first one. E, we got to think back, what I wrote down here. A is equal to 10, right? F is equal to 15, so E must equal 14. So I need to write 14 into binary. So, right, I'm going to think of the highest power. So 8. The next power is 4. 8 plus 4 is 12, so I'm still good. Next power is 2. I'm at 12, right? Add 2 more. That's 14. That's the 14 I need. So that's that part. And then F. And F is really easy. Always remember that F in binary is just all ones, right? It's 15. And that's the highest representation you can get with 4 bits. So that's that conversion, right? And of course, if you want to maybe back convert this into decimal, you can also do that too using what I said. This is 2 to the 11th, right? And 2 to the 11th is typically you won't work with a number this big, but if you had to do a conversion, right? 2 to the 11th, 2 to the 10th, 2 to the 9th, 2 to the 8th, plus 2 to the 7th, plus 2 to the 6th, plus 2 to the 5, plus 2 to the 3, plus 1, right, for this back bit. You would calculate all this, and that's a pretty big number, so I'm not going to do that. It's somewhere in the thousands, so I think you guys went over octal, and octal is kind of the same as hexadecimal, where hexadecimal correlates to kind of the 15 different values, right? 0 through 9 through F. And octal, if you guessed it, uses 8. So 0 through 7, right? And so each octal symbol is going to represent 3 bits, right? Because if you want to find out like how many bits it takes to represent 7, you can do log base 2 7, right? And that should give you exactly, or 8 really, because there's 8 different values with 0 inclusive, and that should give you 3. So let's run through a quick conversion to octal maybe. So let's just do another hex conversion just for the fun of it. FA. So let's convert this to binary. So A, I remember, is 10, right? So how do we write 10 in binary? Well, 8 can fit in there. If we go 4, right, when you get 12, which we don't want, but this 2, right, give us 10. So this is the first 4 bits, right? With hex, we're thinking nibbles, 4 bits at a time. And F, like I said, is all ones. This is the binary representation. Well, what happens when I want to go to the octal representation? Well, instead of groupings of 4 bits, like in hexadecimal, I'm going to think in groupings of 3 bits, right? And, if there's something empty right here, it's assumed to be a 0, right? So what's this number here? We have, this is just 2, right? So we're just going to write 2. This is all ones, right? So this should represent 7. 4 plus 2 plus 1, so 7. And this one, leading zeros are assumed to be 0, or if you need an extra bit, you can sign extended 0 here. So we have 1 plus 2, which is 3. So the octal representation of FA in hex, this is what, the octal is. All right. I think we've spent some time going over systems. If someone has a question, you can ask me. But let's move on to something a little bit more challenging now. So you've probably noticed this entire time I've just been talking about unsigned numbers. And of course, we have numbers that are signed. We have negative numbers. So how do we represent negative numbers? So there's a very clever system that's used called 2's complement. This is how we represent negative numbers. So let's say I want to represent -1. How am I going to do that? So this is the process to represent a number that's negative. So what we're going to do is I'm going to be working with 8-bit numbers here. And when we have this 8-bit number, we're going to have some 8-bit binary number. Always when you have a 2's complement number, you can figure out the sign using this bit, and that's going to come into handy. We're going to see that. But what we're going to do is we're first going to represent the unsigned number binary. So how do we write 1 in binary? That's 8 bits. Well, all these bits, the first 7 bits are equal to 0, and we just have 1 at the end right there. So simple. The next step is we're going to invert the bits. So all the zeros will become 1s, and all the 1s will become 0s. And then we're going to add 1. So adding 1 to this number, right? 0 plus 1 is equal to 1, and all these just carry down. So this number right here, this binary number, is how you represent -1 in 2's complement. All right, let's do another example here. And notice, right, we got a negative result here. You can always look at this last bit. This last bit will tell you if the answer is, if the number is negative or positive, right? So this was negative, right? So if you have a negative answer, the most significant bit will be a 1. If you have a positive number, this will be 0. So I kind of ran through how we would convert positive, how we would represent number and 2's complement. Let's say we get some 2's complement number. So I have a 2's complement, 0, 0, 1, and I want to find out what this means in decimal. Well, first I need to determine, right? The first thing we need to do is we need to determine whether this is a positive or negative number. If I had a number like this, say I had a number like this, I'm going to look at this leftmost bit and see if it's positive or negative. I can see this is a 0, right? So it's positive. If the number is positive, I don't really need to do anything else to it. I can just do my normal way of finding out what number it is by adding the powers of 2, right? 64, this is plus 32, plus 8, plus 4. I add those all up, and I get 108, right? And then I'm done. I know this represents 108. But it gets tricky whenever, you have your number. You're trying to determine what number this is. This is a 2's complement number. And I look here, and this bit's 1. So this means it's a negative number. So how do I figure out what the number is? Well, what I do is I do 2's complement. It's the same thing as we did before. You invert all the bits, and you add 1, right? 1, 1, 1, 1, 1, 1, 0, 0. And now I'm going to do the process I did before. So this is 128, 64. So 32 plus 16 plus 8 plus 4 plus 2 plus 1. What does that equal? So we have 10, 20, 23. So this is 63, right? But as our final answer, remember, we determined at the beginning that this bit was a 1, which means it's a negative number. So this is actually negative 63. That's how we represent this negative number, using this number to its complement. Okay, so let's do some examples. Some addition, subtraction type examples, right? Let's say I want to add two numbers. I kind of showed you adding, but we'll do a more concrete example. Let's say I want to add 7 plus 16, right? You know, to us, this is easy, right? It's just 63. But let's do it in binaries. So let's convert 7 into binary, right? So 7 in binary is 1, 1, 1. And 16 in binary is 15, right? This is 15 in binary. Oops. 16, right? I'm going to go in my head. Greatest power of 2. So I can just put 16 in there, right? And then 0. And then I can add these two numbers together. So this is a very good example, you know, because 1 plus 0 is equal to 0. This is all the same thing, right? Oops. Something. Right, this should be that, right? I didn't move it over enough. Right, so when I calculate what this number is, I get am I still doing something wrong? 7. 16 here, right? Yeah, this should be right. Right, so we're gonna continue here. Right, this is 23. 4 plus 2 plus 1. 23. So, right, that's pretty straightforward. I should come up with a better example here. So let's say I'm just going to create some numbers here, and I'm working with unsigned numbers. So I have this number. I have this number to make it a little bit more interesting. So let's add these two numbers together. So 1 plus 1, that is, you know, in our minds 2, but it overflows, right? Because I can only represent 0 through 1. So 1 plus 1 is actually 0, and I'm going to carry a 1, like in normal addition. 1 plus 1, same scenario here, right? 0, carry the 1. Have the same scenario again, right? 1 plus 1, 0, carry the 1. Well, now I have 1 plus 1 plus 1. I know 1 plus 1 in binary is 0 with a carry, but then we have another 1, right? So this is going to make this one 1. We're still going to have a carry. This one, same thing, and this is going to carry over here. So let's figure this out now. We can convert this back. So this is going to be 8 plus 32, which is 40. And what numbers do we have originally? We had 16 plus 8 plus 3. 17. 8 plus 4 plus 1, which is 13, right? That's 40. 16, 8 plus 3. That was, yeah, so this was 40. This is 20. So we still get 40. So that all makes sense. All right. So that's just kind of addition in general. So how do we do subtraction, right? Let's say we want to subtract two binary numbers from each other. So I have, let's say I want to do subtract this number from this number. How should I go about doing that? Well, typically I say, z is equal to x minus y. So if I have two positive numbers here. I know they're positive because we have a 0 in the most significant bit. So what I can do is I can turn one of them negative by using 2's complement. And that's how we're going to achieve the subtraction, right? So I'm saying I'm going to subtract this number from this number. So I need to convert this number into a negative number. And how I do that conversion, right, as we explored before, is just to do the 2's complement of it. So invert the bits, and then add 1. So we get this number right here. So taking this number, right? Okay, keep that in mind. So I'm going to take 0, 1, 1, 1, 1, 0, 0, and I'm going to add them. And adding a negative number is like subtracting the positive number. So we get the same effect. I'm going to do this addition. 1, this is 0, carry the 1, 0, carry the 1, 0, carry 1, 0, carry 1. 0 and 1 is going to hang out here. Since I'm saying this is an 8-bit number, this carry is going to get discarded in this case. And so what I'm left with is this number, right? This should be 7 in decimal. So let's kind of check our work here. Right? So this was the original question right here. Subtract this number from this number. Well, what's this number here? This is, just very quickly, I'm going to say this is 124. This is 117. Were our two numbers. So that makes sense. I think I flipped them around. This is but that's how you use 2's complement to do a subtraction. So, any questions so far? No questions about kind of two's complement and negative numbers. I'm gonna talk very quickly about fixed point numbers. So right, we know how to represent decimal. I mean, sign numbers now with two's complement. Now let's talk about like a fixed point. And when I say fixed point, is I'm gonna define some point in my binary number where I'm going to start representing fractional numbers. So let's say I have this binary number. I have this decimal right here. And what that means is everything here is like we've talked about before. This is 2 to the 0. This is 2 to the 1. This one right here is 2 to the third. But right here, this actually represents 2 to the negative 1. And this number represents 2 to the negative 2. And 2 to the negative 1 is 1 over 2, which is 1/2, and this is 1/4. So that's how we're going to figure out what this number is. We're going to start as before. This is 8 plus 4 plus 1, which is 13, with the decimal. And what goes behind here? Well, 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4. This is 0 right here, so we're just going to have 1/4. So this number is 13.25. Let's do another one here. So let's say we have, this is in binary. This is an 11 and 1/1000th. So let's do this part, right? This is 2 plus 1, which is 3, the decimal. And so this place right here is 2 to the negative 3. So it's 1 over 8 is 0.125. So this is the decimal, right? All right, so let's say we want to go the other way around. We're going to start with a fractional number and we want to put it into decimal. Or we start with a fractional decimal number to binary. A lot of times, it's kind of harder to kind of fit the greatest power of 2 to the minus something in it. So we can use a technique called the rule of successive multiplication. So this 57 is relatively easy to figure out with our old method, right? Greatest power of 2, right? 32 plus 16. We have 48 plus 8 plus 1. So we got these powers. So I'm going to write that down as 1, 1, 1. So right, we need to figure out what the decimal number is. So what we can do is apply this law of successive multiplication. How we're going to do that is we're going to take the fractional part, so we have 0.6875, and we're going to multiply this by 2. And calculate. Multiply that by 2, we get 1.375. What I'm going to do is I'm going to take whatever number was right here and remember it. So that's a 1. And I'm going to multiply the number by 2. But I'm only going to multiply the fractional part. So I'm not doing 1.375 times 2. I'm doing 0.375 times 2. So once I do that, I'm going to get 0.75. I'm going to circle this. I want to keep whatever the non-fractional part is. And I'm going to multiply 0.75, right? Only multiplying this part by 2. So I get 1/2 here. Or 1 and 1/2. I'm going to remember this. And I'm going to multiply 0.5 by 2. And I get 1 here. Now you can see here the fractional part is 0. I can multiply it by 2 all I want, and I'll just get 0. So I have these 4 numbers. So what do I do with them? Well, I just take this one, right? And that's going to go right here, and so forth, 0, 1, 1. And that's how you can figure out what bits are in this position. Okay, I think we've elaborated on the binary number systems enough at this point. So we're going to move to Boolean algebra. So Boolean algebra is a way to express ways to write equations that can be expressed using logic gates. So we have several logic gates, right? We have AND gates, OR gates. We have variations of, or an inverter, right? And then we kind of have the composite gates, the NAND, and the NOR, and then exclusive OR also. So, right, we can, define what these do, right? This is just a very synopsis. So an AND is 1 only if A and B equals 1, right? So with an AND gate, in order for the output F to equal 1, both of these inputs have to be a 1. And if we were to write a truth table, so what a truth table is it relates every combination of the inputs to the outputs. This truth table is only true whenever both inputs are equal to 1. So this is the only case where this is true. So with the OR, this is true if A or B equal 1. So this truth table is going to look like this. 0, 0, 1, 0, 1, 1. There's no 1 here, so 0, 1, 1, 1. It's kind of the opposite of the AND gate, right? I only need one input to be 1 in order to get my output to be. An inverter, it takes whatever the output, the input is, and inverts it. So if you have a 0, that goes to a 1. If you have a 1, that goes to 0. AND gate, right? It looks like an AND gate with an inverter, and that's exactly what it's doing. It's saying, this is the Boolean equation for it. It's saying we're taking the AND of A and B and inverting it. So what does that look like? Well, it's the inversion of the AND truth table, right? Right, normally this would have been a 0 if it was an AND gate. Well, it's actually a 1 now. And these are all 1s except for this one, right? It's an inverted AND truth table, right? When we had the AND truth table over here. We have just inverted the table with this function. NOR, it's an inverted OR truth table, right? This is OR, this is NOR. So when we had this going on, we actually have the inverse going on now. And a NOR looks like an OR with this little dot right here that denotes the invert. And if I didn't say this before, inverter usually looks like this in a circuit diagram. And XOR is a little strange, so it's an exclusive OR. So it will only output a 1 if only one of the inputs is 1. It has one of the inputs has to be exclusively 1. That's where we get the exclusive OR. So this is 0. Only one input's a 1 in this case, right? It's a 1 in this case. But if both inputs are a 1, we have a 0. So that was just a quick synopsis of the logic gates here. So let's talk about Boolean equations. Generally, we can write combination of ands and ors like something like this. So, you know, something that looks traditionally like a multiply, that's an and the plus is an or. And the only strange ones to look out for is if you have like an XOR usually, that's represented by this symbol, which you probably will not see that too often. So what are some properties of Boolean algebra you should know, right? We know when you went to school or elementary school, you learned about distributive, commutative properties, right? We're going to kind of go over those. So the commutative property, right, is x and y. It's the same thing as y and x. When you're doing an and, it doesn't matter what order you. And the same thing goes with, you know, x plus y or x or y. It's the same as y or x. It doesn't matter what order. The distributive property, right, is you can essentially just distribute terms in Boolean algebra, right? So this is the same as xy plus xz, like distributed term. The plus is, the or is also distributed in this, which is a little bit different from what you would traditionally think of, right? So you can write this as xy. I'm going to distribute this x to this and term, right? So x plus y anded with x plus z. This is also valid statement. And I'm just going to list out some general properties that you should know. So anything ORed with a 0 is just itself. Anything ORed with its complement, you know, the inversion of it, is always 1. And that makes sense, right? If x is 0, this has to be 1, and anything ORed with a 1 is 1. And if I did the vice versa, I would get the same result. Anything ORed with itself is just itself, right? And anything ORed with a 1 is always equal to 1. So how does this look like with the ands? Anything anded with a 1 is just itself, right? Anything anded with its complement is always going to equal 0, right? Because these always have to be opposite, and you have to have both the inputs to be equal to 1, which you get a 1. Anything anded with itself is just x, and anything anded with a 0 has to be 0. So these are some properties we're going to know, and we're going to be able to use these properties to do logic simplification, essentially, and be able to kind of break down equations manually. A little bit later, I'll get into K-maps, and those will be a more visual way, a little bit easier way of doing logic simplification. But for now, we're going to practice just using Boolean properties to get down to a simplified equation. So let's talk a little bit about SOP and POS. So what's SOP? This is some products. That's what we usually use. That's what we like to see. Sum of products is something like this: AB plus BC plus AD. You have groups of ands, right? And they're separated with these ors, right? And in a circuit diagram, right, you'd have groups of ands, and all the results of the ands are going to be OR together to get you your F output. And what we'll learn later is that in a sum of products equation, each of these terms is called a minterm. And a minterm is the combination that makes the equation equal 1, right? So essentially what's that saying? In this term, like we have the term AB, it's saying anytime A is equal to 1 and B is equal to 1, well, F, the output's also going to equal to 1. And same thing here, you know. If I have B is equal to 1 and C equal to 1, F is always going to equal 1. In that case, those are our minterms. And these minterms express, this term expresses multiple combinations that can happen, right? Because we know from our Boolean properties that, you know, we have a 4 variable thing here that BC, right? You know, we can put an implied 1 here, and that implied 1 we can write as D plus D naught, because anything complemented with itself is just 1. So we can express this as BCD plus BCD naught, and with this one, there's always an implied, you know, A plus A naught here also. So if I were to fully expand this, you know, I'd have A, B, C, D plus A naught, B, C, D plus A naught, B, C, D naught plus A, B, C, D naught. So essentially, the term BC here actually relates to 4 different minterms, or 4 different combinations of all the parameters that equal to make the function go to 1. Okay, and so let's go back to POS here. So that was SOP, right? Remember, we have ands that are separated with ors, and each term is like what's the variables need to go to, right, in order for the equation to equal 1. So POS is kind of the complement of that. So in POS, we have groupings of ors that are separated by ands at the second level. So plus B, B plus C naught. So this is, you know, a 3 variable function here. And what this is describing, it's describing the max terms. So the max terms are the terms that make F go to 0. And so you generally don't see this as much, and I'll kind of go back to POS whenever we're going to do K-maps a little bit later. So let's do kind of an example of using algebra variables. So I'm going to draw a pretty big expression here, and we're going to reduce it down. C, B, BC times A plus B. Let's put this in brackets. More brackets. plus ABC. So we have a big and nasty Boolean expression, right? And we want to break this down into something more manageable. So we're going to just start by using some of our Boolean properties we described earlier. So I have this A right here, right? I'm going to distribute this A to all these terms here, right? So remember, anything ANDed with itself is just itself. So A and A is not going to do anything because I already have an A term, right? So this is going to become A, B, C plus, right, AB plus ABC because I'm ANDing BC here plus B, C plus ABC. So we've simplified it a little bit, and really I don't need this parenthesis anymore. So I'm going to do the same thing here. I'm going to distribute the C to all terms. So ABC is going to stay the same because anything ended with itself is still itself. This is going to become ABC. This is ABC. This is BC. And then we have this ABC at the end here. Well, another Boolean property I said is anything ordered with itself is also just itself, right? So all these ABCs here, they can go away from our expression. So we have ABC plus BC. So now we're, this is a lot better than what we had before. So can we possibly apply some kind of way to make this simpler? So one way we can do a simplification here is we can kind of look at things here, right? So this like BC encompasses all the, if something's BC, right? If we have B is equal to 1 and C is going to equal to 1, the function is going to be forced to 1, right? But this ABC, well, if BC is already equal to 1, 1, this term already, describes this. So this A is kind of redundant, or it's not being helpful. It adds more complexity, right? So a lot of times, if I want to simplify something just using Boolean algebra, I like to completely expand it. I like someone just said something in the chat. Christopher, BC, A plus 1. Right, yeah, that's the same kind of expression, right? And so what he's saying is that the BC can go away here. Which is exactly right. So what he's doing is he's factoring out the BC. A plus 1, right? And then we know that anything ordered with 1 is just 1 itself. So you have BC1, and that's just equal to BC. So that's how we would do that logic simplification, just using Boolean algebra here. So let's do, that was kind of my example on just using Boolean algebra to do a simplification. We'll use K-maps a little bit later. That will make things a little bit easier to do. It's a more visual way of doing the same thing. So let's do an example, this time using a truth table. Like I said, truth tables are ways to define the function of a Boolean, of a circuit usually, and they enumerate all the different possibilities and give you the outputs for every different possibility. So let's say I'm given this truth table right here. I want to write the SOP equation. So how should I do that? Well, I can just write down all the min-terms. And remember that the min-terms are all the terms that make the function go to 1. So this is one of my min-terms. This is one of my midterms right here. So I'm going to write those down, and I'm going to separate them with an or. So I'm going to have, this is x naught, right? X is 0, and then y is 1. X naught y, or x y. Now, can this be simplified anymore? Yes, it can, right? It's kind of the same thing we did earlier. I can, leverage that distributive property and, factor this y out, and then I have this. And from earlier, we said that anything ORed with its complement is always equal to 1. So we just get y as the result. So another example here, let's say we want to go vice versa. We have an equation, this, equation like this. We want to make this into a truth table. And see, I have 3 variables here, so I need 3 entries in my truth table. And I see these are fully expanded, so I know that they're only going to correlate to 1 entry in my truth table, right? So f's, right, I'm going to have zeros everywhere except for at this point and this point. So this is 0, 1, 1. There, that's it. And then I'm going to put another 1 at 1, 0, 1. And all these are going to be 0, right? Okay, so how about we do kind of one more example with Boolean algebra. Let's say we have an equation like this. And we want to do a simplification here, right? Well, I see right here, I could factor out, the x, y, and then get this right here, right? But what about this one? Can I factor this with anything else? Well, if you look closely, right, I could factor this out with this one, right? Because this also has x naught and z. This also has x naught and z. So I could factor out an x naught z also, right? And have y plus y this. And what I'll get is xy. This is equal to 1. Anything ended with 1 is just itself. And this we get x naught z. And if I wanted to maybe write this, as the actual circuit, right? This is SOP. I have 2 AND gates. And the output of these AND gates are going to go into an OR gate. This is the function output f. And I'm going to have x and y here. So both x and y are being inverted to the circuit. And right here I have z. This is going to go to this. And we're going to take the x naught here, right? and feed it into that gate. Maybe I should pause here. I've gone over a lot of things. Any questions so far? I think at this point we can jump over to doing K-maps and explaining how we should solve K-maps. Alright, I didn't see anything, so let's move on to K-maps and how we should go about doing K-maps. So a K-map, I just went over a few examples of we essentially did some factoring in order to make some variables, right, b plus b naught, those we wanted to make things go to 1, right, and to simplify them out. And essentially what we can do is we can create kind of a chart that will help us do that visually, and that chart is called a K-map. So a K-map typically is between 2 to 4 variables. Usually will probably be like that in this class, and really 3 to 4 variables usually, right? Or I guess you can do two. And so how you're going to make your K-map, right, is let's say we have some function of 3 variables, a, b, and c, right? How should I draw my K-map? Well, I'm going to create, for 3 variables, it's going to kind of look like a rectangle. So here on this column, you're going to have b, and on this column, you're going to have bc. And what this is doing, this is numbering all the different combinations of BC you can have and all the different combinations of A you can have. Now look right here. This is kind of weird, right? I went from 0 to 1 to 3 to 2. And you have to be careful of that when you're numbering this K-map. And the reason why we do that is we want each adjacent cell to only change by 1 variable. So the only difference between BC here and BC there is just a change in C. Right? I only want one of the variables to change at any one given time. That's something called gray coding. And that's why the K-map works, because if I have an expression AB plus AB naught, you can see between these two terms there's only one single bit change, and that's what allows me to do this factoring maneuver and results in a simpler expression. So that's why the K-map is numbered like that. So always remember, to number your K-map rows 0, 1, 3, 2, right? That's important. And so we can express, what number, what minterm we have in each cell, right? Because this is 0, 0, 0. So this is 0. This is 0, 1, 1, so that's 1, 3, 2. This one's 4, 5, 7, 6. So this is how we would build a K-map of size 3. And so if you have some expression we want to simplify, let's say we have, just going to make one up right now, AB plus, let's do our example we just did, right? This is a very simple example. You probably could do this without a K-map, but let's go ahead and do this with this K-map right now. So AB, so what terms are, what numbers or terms is AB gonna make the function equal to 1? Well, it's anytime A is equal to 1, so this row, and anytime B is equal to 1. So we see right here, A and B are both equal to 1. So I'm going to put a 1 right here, right? So when the function is going to go to 1. And I see also right here, A is equal to 1 and B is equal to 1 right here. So I'm going to put a 1 right there also. So I've done this term, right? Let's do the second term. Well, A is equal to 1 still, so I'm still going to be looking at this bottom row. And be circling when B is equal to 0, which is, I got this backwards. So these cells, right, corresponded to, these cells correspond to when A is equal to 1, B is equal to 1 here, right? These two cells are when A is equal to 1 and B is equal to 0, right? This is B. This is B. Backwards there. And so we're ready to do our solution with the K-map. So with the K-map, you're searching for what's called prime implicants. And those are groupings of the power 2. And the bigger grouping you make, the better your solution is going to be. So you always want to try to find the biggest prime implicants. So you want to find groupings of contiguous 2, 8, 4, 16, however big you can make them, right? And so they have to be, you know, in one region, right? So this right here, this group, this is group of 2. This would be a valid implicant to make here. But it's not the biggest power of 2 we can make, right? Because if we look over here, we could circle all of these right here, right? That's grouping of 4, and that's the biggest prime implicant we can make with that. And so how do I write down what this term simplifies down to? Well, I'm going to look at, so I made this big group of 4, this prime implicant. Now I'm going to look at what variables stay the same throughout the entire implicant. Let's look at this row. Well, throughout this entire grouping, right, does A ever change? No, it stays 1 the entire time. So I'm going to write down A. Let's look at BC. Does B or C ever stay just a constant value? No, they flip from 0, 0, 0, 1, 1, 1, 1, 0, every single possibility. So those are eliminated out. So I get the result A with this K-map, which makes sense, right? Because if I factored out the B like before, let's simplify to A. So 2 ways of arriving at the same answer. But typically your K-map is going to be a little bit easier not to mess up on, since it's a visual method and humans are good at visually locating things. So just as an example, right, let's say we have, you know, another 3-variable K-map, and we have something that looks like this. How would we group our prime implicants? Well, let's look at this. You know, it'd be nice if we had a 1 right here, because that would give us our nice group of 4, but we don't. So we have to make something else work, right? I've got to circle every single one. So in order for the K-map to work, you have to have every single one in a circle. Okay, so you're going to keep on trying to make prime implicants until you've circled all the ones. So I'm going to try to find the best groupings here. So I know I can circle this one, right? This looks like a good option, since I can't make anything with the 4. But what about these two? They're kind of by themselves. And what you need to know with the K-map is that the sides wrap around like this, and the sides up here will wrap around like this. So what you can actually do is form a grouping like this, right? Between this one and this one. Because the edge of this cell is technically connected to the edge of this cell, so you can create another grouping like this. And so what would this simplify down to? Well, let's look right here. Does A ever change? No, it stays on the row the entire time, and A is equal to 0, so that's A naught. Let's look at this. Does BC stay the same? Well, from here to here, B changes, right? So that's going to get eliminated. But C stays 0 the entire time. So this term generated from this prime increment is A naught C naught. Can add our plus, right? We're going to look at this one. A stays constant the entire time, so I'm going to write it down. And we see that B stays the same and C doesn't. So we're going to write down B. That's what this would simplify down to in this situation. So there are no questions. I'm going to go ahead and move on. Let's go to a 4-variable K-map, something a little bit difficult. So let's say sometimes you might be given just the min terms, like I said. So this is saying this is the sum of the min terms. So these are all the terms that make the function 1, right? Now let's say we have this grouping. So I have these midterms, right? And this is a function of w, x, y, z. And so what each of these numbers mean is this is the terms that make the equation S of p go to 1, right? So 1 is going to be wx. It's going to be this, right? 0, 0, 0, 1. And this 3 term is going to correspond to 0, 0, 1, 1. 3, right? Which is w. X naught, y, z. That's what the sum of midterms means. So let's build our K-map here. So since I have 4 variables, I need to make 16 like this. And right here, I have wx and I have yz here, and I'm going to do my numbering 0, 1, 3, 2. Let's remember that. 0, 1, 3, 2. And for the sake of simplicity, I'm going to number them. So 0, 0, 0, 0, 0. This is 1. This is 3. This is 2. This is just the same as last time, right? I go here, 0, 1, 0, 0. That is 4. 0, 1, 0, 1. That is 5. 7. 6. So here I have 1, 1, 0, 0, which is 12, right? This is 1, 1, 0, 1, which is 13. This is 1, 1, 1, 1, which is 15. This one's 1, 1, 0, which is 14. Right here I have 8, 9, 11, 10. So I have all my grids populated with numbers, and I'm going to look at these and I'm going to put a 1 wherever there's a midterm listed. So I'm going to put 1 at 1, put 1 at 3, 1 at 5, at 7, at 13, at 15. So how should I group these? So remember, I'm always trying to make the biggest groupings of power of 2. So I can make plenty of groupings of 2, right? But I always want to strive to make the biggest grouping. So let's look at 4s, right? I can make groups of 4 here. I could also make a group of 4 right here. I can't make a group of 8, right? I only have 6 ones. So I'm going to try to make groups of 4. So with this one, it doesn't really matter. So I'm going to circle this group of 4. Okay, so I have a group of 4 here. So I need to cover these ones still. It may be tempting to make a group of 2 here, right? Because 2 left. But remember, we're always trying to cover variables with the largest grouping of 4. And if you do an overlap, overlapping is allowed as long as it's making the equation simpler. So instead of making a grouping of 2, I can actually make a grouping of 4 like this instead, and that will result in a simpler solution. So we're out for the simplest solution here. So what is this going to turn into? this case? Well, you have two groupings of 4, and we're going to run down how to do it. So let's do this like top set of 4 right here. So I see that W stays the same and X changes, right? W goes from 0 to 0, X goes from 0 to 1. So we're going to write W naught as this term. Let's look up here. What stays the same, what changes? Well, Y goes from 0 to 1, so that gets eliminated, but Z stays 1. So this term, represented by this group of 4, is W naught Z. Add an OR right here. Let's look at this grouping of 4 right here. See that X stays the same in this case. It goes from 1, 1. W doesn't stay the same, goes from 0 to 1. Okay, let's look right here. See that Y is changing, but Z stays the same. So this is our simplest K-map. And this would be the simplified version of this equation. Any questions so far? Okay, so sometimes you'll have don't cares included in your equation. So let's do an example with don't cares. Don't cares are essentially like a condition that cannot happen in the circuit. So we don't really need to make sure they have coverage, but if we can include a don't care that makes our groupings bigger, we want to do that, right? Because it will result in a simpler equation. We're always trying to make these groupings that cover everything. So let's say, f of w x y z to sum of midterms. Here 4, 6, 12, 13, 14, 15. Plus don't cares. And let's make 9 and 11. So right, we're gonna generate our K-map again. I'll just go through it relatively quickly this time since we've setting before. Alright, set up our K-map, and now I'm going to put our midterms in. The midterms in as 1, so 6, 12, 13, 14, and 15. So this is what this is looking like, and then I have my don't cares. Now my don't cares I'm going to denote with an X. So let's figure out how to simplify this equation, right? So we want the biggest grouping of power of 2. So can we create a group of 8? I'm not really seeing a continuous region of 8, so let's go down to 4. What groupings of 4 can we create? Well, you could create a grouping of 4 like this, right? But what about these? Can we create a grouping of 4? And this is where you can say, oh, right, I can group 4 wrapping around like this, right? So let's do that. So now we have, a lot of times in your K-map, you're going to have different types of choices, right? About what you can group. I have a group of 4 right here that I could group, and that would be perfectly valid. And I would have all the required coverings. Remember that don't cares, you don't have to include them in your covering, right? You don't have to cover them, but you can include them if they make the group better, right? Another valid choice is to circle this group of 4, right? This makes a group of 4, and we include the don't cares. Now, if I include this one or this one, it doesn't matter which one you do. It's a matter of choice because both result in a group of 4. One isn't better than the other one, so to say. So just for demonstration's sake, I'm going to pick this one. So let's go over and create our equations, right? And every time you go up a power 2 in your grouping, so if you have a grouping of 4, you'll be reducing the complexity by 2 variables. If you have 8, you reduce it by grouping of 2, you reduce 1 variable. So let's run through this. So let's do this kind of wraparound group first. So what stays the same in Wx? Well, x is staying the same, right? And then what's staying the same in yz? Well, we can see that it stays z naught the entire time. So this is x z naught. Bored with this, use this group. What stays the same in Wx? Well, W is staying the same. And what's staying the same in this yz? Well, I can see that z is the parameter staying the same. So this is our simplified equation for this. So I'm kind of at the end of the things I wanted to talk about tonight. If anyone still in chat wants to ask a question or see a particular example, we can do that now. If there's no further questions, we can all log off now. So I'll kind of pause here, take any final questions, suggestions, and there. Okay, so you guys do Shannon's expansion. So yes, I can do a Shannon's expansion. Shannon's expansion with max term. Are you talking about a Shannon's expansion with just max terms, or maybe example of something else using max terms? So yeah, let's talk about Shannon's expansion. So typically with a Shannon's expansion, let's say we start out with an equation like this. This equation is equal. what Shannon's expansion is that through every iteration, I'm going to try to pull out a variable, and I usually do that from most significant to least significant here. So what I'm going to do is I'm going to kind of separate this out, right? And I'm going to first pull out an x, an x naught, and then I'm going to write down what the resulting expression is, and then I'm going to go into here. So I'm going to look at this first, this term first. Does this term have an x in it? Yes and no at the same time, right? Because there's a 1 right here, and a 1 can be, x plus x naught. So really, I can include this term in both x and x naught, right? It's valid for both. Same thing with this term, right? It's kind of if the variable isn't there, it applies to both of them. And we see that x only exists right here. This is x right here, and it has just a z. So we're gonna put that z right there. And we're gonna continue to do this. So we're gonna have the same expression, but in each of these parentheses, we're gonna do y and pull out something. That's y not. Pull out something. Plus x, y, pull out something, plus y not. So let's work in this parentheses. If I pull out a y, what's gonna happen? Well, I'm gonna go z right here, and since z is by itself, it can also go in that spot also. But like I said, anything ORed with this, itself, it's just itself. So I'm just gonna leave that as a z right there. This y naught, z naught can go in there, and we also have the z right here, right? But when we do that, that can just simplify to a 1. Right here, working with the x naught, we have a z naught right here. And we have a z like this. So if we were to write this down, the full Shannon expansion for this is yz plus y naught 1, right? Plus x naught y naught z naught plus y z. Alright, so that's with the SOP equation. So let's move to POS, perhaps. And so I've never done a Shannon expansion with the POS, but I say we can work it out here, and you guys can check me, right? We can kind of think this together. Maybe forgive me if I stumble through this, since I've not done this before, but we're gonna try, right? So let's say we have some function. I'm just gonna make something up here. Something. We have a plus b plus c x not c plus a naught plus b plus c. You have some equation like this. Right, and so kind of everything we do here with the old SOP Shannon's expansion, we're gonna do the opposite of that. So let's see how we're gonna. See if I can make some notes here. Okay, so um, let's see here. So we want to try to start pulling out a variable such as a, right? So we want to have some variation of a naught. We want to have a way of writing this still in a POS form, but still kind of extracting it out. So we want these to be separated still by this sign. So, has your professor done a POS like Shannon expression in class? I'm just saying this because I've never seen this one, and I'm gonna be honest, I don't know how to do it. I think it was homework, but maybe I was misremembering. So, how about? I'm not entirely sure how to do that. I would try to. Sorry about that. Uh, yeah, I will pull up the actual question. Okay. Use Shannon's expansion to reduce the Boolean expression. It does not have to be private. So I don't think you showed it in class, Steve. Right. There's only one odd term. Right. Okay. Um. Yeah, I'm not entirely sure how to do this, so um, maybe I'm just look at the key right. So I'm, I'm sorry about that, but that wasn't something we typically just did Shannon with the SOP. So that's about the extent of my knowledge. But maybe if you have the question, how about this? I will post an example POS. I'll look up how to do it and I'll post it in the IEEE tutoring chat for those of you that want to still know. But I might need to look it up real quick offline. So I'll post a follow up of this question in the chat on the IEEE Discord for those who are interested. Yeah. All right. Any more questions before we get off here then? It's Bobby, my name. All right. So I hope that was helpful for you guys. It's a little bit harder for me to kind of give you pertinent information because when I took this class, we had Dr. Dodge, who is retired now. So, I kind of had to give a more general kind of spiel, but I hope, some of these practice problems were useful. You guys do well on the exam, and I will look up. You kind of got me off guard. I will look up how to do Shannon's expansion EOS, and I will try to submit that to the IEEE Discord chat in the tutoring session, so you guys can see an example of that. So I'll probably upload that in 30 minutes once I figure out how to do that. So no more questions. Log off here. Thank you guys for coming and listening. I hope you guys do well.